I'm Steve, platform solution architect from Intel, and I'm mainly focused on high performance networking, so especially DPDK, yeah. And today I will give my topic is about VIRTIO Net. And this is our teamwork, so I represent for the DPDK engineering team to be here and present the work we are doing on the I/O virtualization. Oops. Sorry. Yeah, my talk includes 3 parts. First one, I will give an introduction on the background and the motivation why we are doing this. And then I will introduce what is vhost data parse acceleration and how's the design and the hood, and then what's the implementation software proposal there. And in the end, that I will give a summary on the future work. Okay, yeah. As we know that, before I starting this, I just give a context setting is that we talk about VIRTIO Net here. So we're on the QEMU and the KVM perspective. So any thing I talked about the PV is related to VIRTIO. So VIRTIO as a virtual host interface is being widely used in the cloud and even in the cloud infrastructure. And but when we are going to run some virtual network functions in the guest, like some DPDK-based firewall or DPI in the guest, that current performance that is not not good enough. But under NFVI, which is the infrastructure for NFV, that DPDK is being used to promote the performance on the host side to make a better software vSwitch. And that's the cloud vSwitch situation, cloud vSwitch as our NFVI. And a few products comes into market, which is usually called is Smartnic, which is going to offload some forwarding decision on the card, so that you can spend less CPU cores to the forwarding and get the directly packet I/O from the hardware go to the VM directly. So, and then the faster parse in host software tends to be our faster parse in the hardware and faster slow parse in the host side. Is that perfect? Actually, for those virtual appliances which can easily upgrade the driver or change the image in their VM, that's probably good because you can take a physical host interface and get the packet directly. But for those VM or for those virtual appliances building on top of VIRTIO, or even it's no way for you to change the driver there, you are suffering. And then the idea was that, okay, you keep the fast parse in the switch silicon or the Smartnic, and then you still have a faster slow parse in the host side using the CPU to do the further acceleration. And then your VIRTIO just connect with the software switch directly. Okay, that is good. So your stock VM can be no change and running in that infrastructure. But how about for the middle box, like the green one? It's built on top of the VIRTIO, but he also want to have the performance upgrade, but do not want to be aware about the backend change. So if that depends on the traffic, is most east, west, or north, south. So if it choose some service level assurance that I need higher performance, essentially on the backend that you can associate our virtual switch with our physical queue or physical NIC. Then you get a one-to-one mapping. So one-to-one mapping is a much easier way to do like the zero copy. On that time, okay, you get one virtual interface and one hardware queue or interface associated in one-to-one. And okay, as I said, there's a few directions. One is that you still have the software relay to do some, you allows to do packet buffer zero copy, but you still keep the descriptive translation on the host CPU. And another way is that, what if you have a hardware, the hardware is vring capable, who can enqueue and dequeue to the vring directly. So the talk today and talk about the topic today focus is on the second direction. So once you have a hardware which can have the ability for the vring access, what's the next impact for the software? Okay. What is VDPA? VDPA is data path acceleration for the vhost. So we know that this is the acceleration using acceleration on the backend side. So it is just a method that for the PV device to do the direct packet I/O with its associated accelerator. So if we look into the detail, what it is actually essentially it is a decouple the data path and control path of a PV. So for the control path, it remains to be our emulated device in the QEMU, but it is associated with our accelerator or a device in the backend side. On the data path side, that as the accelerator has the ability to access the ring, access the vring, so you can essentially do the data pass-through to the guest. So on that time, it's not a whole device pass-through, but instead of it's a data pass-through. So why we're trying to do this is that if we review the proprietaries in the PV and the device pass-through, if we assume that one virtual device always associated with one physical device, that almost almost the things that we want from the device pass-through actually is the performance. We are not so much care about what exactly the device config space or what exact device specific register it is, but we care about the data path performance. So that's the definition for the VDPA. And so we also assume that you have an accelerator, which it has the minimal feature set, which is you have the ability to enqueue, dequeue the vring, and also recognize the vring format just to follow the virtualized spec. And people may ask, so if you already have a virtual switch, a virtual I/O capable device, why not just do the device pass-through, and you are trying to just pass through the data path? Here's some fact is that first, VIRTIO is a spec. It's quite good. It's growing spec. It changes in some steps, and it's also unlikely to force that individual hardware vendor to always follow our spec, because if we compare the virtual function and the physical function has more featureable things, and it has a lot of metadata, which is not a virtual function need to carry about. So that's the fact. And also, if you're doing device pass-through, you get all the properties inherit from the device pass-through. So, and I'm not going to mention a lot about the limitation on how under Live-migration, and because we all know that. And the one thing I'd like to highlight is when we are trying to do these POC is that we found, so from version to version, VIRTIO on the control path is slightly different. So like for the 0.95, actually you can't directly map device to the guest because it's the config register access is port I/O based. So you only can device pass through like 1.0. And then we rethinking the things. Is that so necessarily that you need to pass the whole device? Why not just pass through a set of the device? Like what you care about? You just care about data path. What is the data path? Why we not define the data path and just pass through data path and keep all the device configuration emulated? Okay, and also the disadvantage for device pass-through if we're doing on VIRTIO is that the beauty of VIRTIO is that you have a front end and a back end. So front end, you can keep that unified interface, but on the back end, that you can have diverse choice. Like today, that we have the vhost net in the kernel, and we also have the vhost user in the user space. So DPDK is a lot of work is doing actually using the vhost user channel. So we don't want to lose that diverse. And then the next, what's the VDPA design? So here's a high-level picture for VIRTIO, pick up the critical issue that we care about. So first, the control path. So the control parse, the config space register and the device specific register are trapped to QEMU, and the QEMU follow up with our emulation function call, which goes through our vhost request. And the vhost request can using different channel like vhostnet or vhost user. And that is the dash line in green. And then what is the data path? First is that the vring is located in host memory, and there can be enqueue and dequeue either from the host from the guest side or from the host side. And this is like the DMA. The interrupt notification is QEMU inject the interrupt to the guest, and so vhost use the IRQFD to issue that notification. And the kick goes through the IO event FD. So this is all the things data paths care about. And then what's the change if we are going to do VDPA? Okay, now we assume that there's a new device. There's a device comes, but it's not as I said, it's not necessary to be our full function or volatile spec defined device. That just need you have a device and you have some piece of logic that can have the vring capable. That we call it is accelerator, vring capable accelerator here. And then first things we care about data path. If we see data path, the backend enqueue and dequeue tends to be our DMA enqueue and dequeue, like DMA write, DMA read. And then we can leverage IOMMU to do the address translation, not like what we are doing today in CPU side. And for interrupt, we can do just the same like the device pass-through. So associated with our VFIO interrupt event FD with the IRQFD. So if you're lucky, and can have the post interrupt in your platform supported and also qualify for the IRQ bypass, then you can share benefits of the post interrupt, and you won't get too much VM exceed by this one. So it's almost the same as device pass-through. Then for the doorbell kick is the thing is quite have two ways in their volatile. For older version 0.95, that is a port IO based. So you always get VM exit, and so you need a software relay on the host side to relay the doorbell and set to the accelerator device. Or if you have a new version supported in your guest, that is lucky, so you can get MMIO directly mapped. Then any doorbell kicked in the guest, you are directly through the EPT and to the hardware. That is perfect. Then if we review this picture, we will see, okay, the new one introduced into the diagram is the device acceleration device. So device need a device framework or driver. Where to put the driver? This is a problem. So for the vhost user, okay, it's quite easy. So you have a user space device framework there, like you can use DBDK just to get enough metadata, then DBDK while the VFIO then program something there. But you still need some QEMU support for the metadata transaction. For the vhostnet, okay, that is inside kernel, so it is never associated with our driver directly. Instead of that, it is talk with our either dev. But it's so how to make that happen in the kernel side? That also a topic in my session. And after the data path, that we back to the control path. So data path is quite easy. Actually, in your runtime, they are just a guest CPU and the device talk each other. But for control path is you make a lot of things to provision the context that data path can happen. So if we review the control path is that any device control access that you drop to QEMU and you follow with our emulation core via the vhost request, then we have a few backend choice. You have a backend type. So syscore for the kernel, vhost user for the user space. And as we just introduced in the data path side, that we missed something in the front end and back end to get synchronized on the metadata. So the design is what's the software piece the design we'll touch is, first is for the vhost user, we need to do some extension to get some necessary metadata. The second one is on kernel side, how we support that and not change too much on the existing vhost net. So we introduce a new channel. So the new channel is still represented for vhost request. So you build a new channel, you can carry the vhost request, but that request is not carried by a function, not carried by just a syscall or like a socket message. It is built, the request, the vhost request is built based on our device layout. But the device is not a real device, but it's a software-defined device, which leverages the media device framework. Then, if we do this on the data path and control path, then review what we need. We actually trying to build the high performance, want to build the PV volatile device to get the performance improvements, but also have the legacy feature support like live-migration. So live-migration, if we're looking on what happened on the backend for the live-migration, so the action all triggered by the guest, all triggered by the vhost request. So different backend actually get the same sequential of the request. And with or without hardware, it really doesn't matter because you get the same sequential, and if you have a hardware, then program hardware. If not, you just do things in the software side. Then the vision we are going to see is, okay, you now have a different NetApp or different backend. So what about, from the kernel backend, upgrade to our user space DBDK-based backend to promote the performance. Or if you have our accelerate vring capable accelerator, you can also transparently upgrade to our vring capable accelerator. So that's the vision, and it's quite good to support that. It's not so much work here to invent here. Then, how our proposal on the software side. So we look at this problem in two pieces. First is user space. Because we are the team working around DBDK, right? So for the user space, what we are missing if we are going to leverage this accelerator. So for vhost user pass, actually we need some metadata to be transferred to the QEMU. The most important thing is VFIO group ID. DBDK is a user space driver, so it takes either the either the UIO or VFIO on the host side. So it's a normal process. So when DBDK initializes it, we can program the IOMMU via the VFIO. But what we can do is that, as I said, the doorbell mapping. The doorbell mapping actually is our EPT table setting. So we need to leverage QEMU. So the message we need to carry, the metadata, is that, okay, by the slave request, we can give FD, the VFIO group FD, pass this one to the QEMU. And then QEMU use this to get some reference count updates. And also using this with some other metadata which identify the memory slot for the doorbell and allow QEMU to set up that. I will talk about more in the next few slides. So the external dependency is only the user space for framework, and DBDK is the one that you can leverage as the user space framework. And then we said that a lot of things can do in user space, but you still need a good enough kernel path direction. Then is second pass for the for the kernel driver. If you are trying to put that accelerator into that accelerator in the kernel, what happens? We don't want to introduce more driver in the QEMU because that is not so reasonable to have a lot of different kind of driver in QEMU. So here we leverage media device. On the QEMU side, we define a new NetApp, which as I mentioned is a new vhost backend, which is vhost VFIO. So introduce the VFIO into vhost tree, and then reuse the existing VFIO QEMU interface. And we define a media device. The media device is not related to any volatile stuffs. So it also not related to any new definition. It's just put the vhost request and just serialize it on our device layout. And the underlayer in the kernel not need any change for the kernel framework. It just leverage the existing framework. And then you put a device driver and register as an MDAV and just add the ops to VFIO device ops, then get things done. And the external dependency for this method is that today's MDAV is not ready yet to support IOMMU, because as we said, we still need using the PCIe BDF to do the IOMMU lookup. And also in a kernel that you need a kernel driver. Of course, you now have a device. Of course you need a driver, but that driver, the request for that driver is registered as an MDAV and aware of the vhost request from the front end side. Then the next 2 pages, I will go in a little bit detail for these two methods, one for user space, another for kernel. Okay, first one is for user space. We are going to define new protocol feature which is called VFIO. And by this VFIO and leverage the slave request, we will let the DBT process to give the VFIO ID and notification inform back to the QEMU. And then have another simple action is just enable accelerator or disable accelerator. Then for the VFIO group FD that in QEMU just do 2 things, quite simple. First is associated the VFIO group FD with the KVM device FD. And the second one is update the GSI routing. But we need to check the second one because we're doing this just to make sure that the token used by IRQ pass-through can get work. But we are looking on why it not work if we not update this one. And the last piece is notification info. So because only the driver know where is the doorbell. So here's the limitation is the doorbell MMI register need to be a page boundary. So we can map the page to the guest. So the things doing in QEMU is that add a guest physical memory slot, so allow the guest instance to kick that address, and by looking up the EPD table, directly go MMIO to the device. For the kernel side, so here's the one new NetApp we are going to define. So define our child device, which is to open our VFI device. But here, the VFI device is really a media device. So you give us this file device address, then you can open that file, and that ID is being assigned to a net using that ID to build a NetApp and hook up with the volatile net PCI. And that VFIO device just represent for vhost request. It's just a device layout based channel for the vhost transport. And in the QEMU side, you need to construct some context for the data path accelerator. Like you need to map the memory region for DMA. You need to set the memory slot for doorbell. You need to associate it with the VFIO events, even FD with RQFD to make sure the interrupt correctly configured. For that, one mentioned that that device, that media device, is not expected to be used by other user space application. It's just defined and being used by QEMU. Yeah, relevant dependency is, as I mentioned, the media device, and also the media device need to support IOMMU. And the vring capable device is a driver that registers as an MDAV, but that a singleton mode because one VF can only register one immediate device here. In summary, so if we review the goal we are going to achieve is that, okay, we have mentioned about how to make a hypervisor native I/O being accelerated by a device. We are talking about VIRTIO NAT PCI. And it's going to transparently support the stock VM, and there is totally no aware in the front-end side. And why it can get better performance is that it's just like device pass-through, but instead of it, it's a data bus pass-through. And it's a live-migration friendly. The infrastructure there just it depends on how you design your accelerator. And in the last, I'd like to highlight is that we are not just saying this kind of like method is only for VIRTIO. So we are thinking about that being a general way to boost the PV device by some accelerator. So the team is rethinking the IO-VT and trying to break through some boundary in order to make a better performance so that virtual appliance in the VM can running much faster. And future work, we are it's now the stage to collect feedback. We haven't sent out RFC patch yet, so we are going to send it first in the DBDK, then the patches go to QEMU. The last one is then to the kernel. And beside that, we are also continue working on enable some IHV device interface, just like you not necessarily have your acceleration on, really is a vring capable, but for any host interface, physical host interface, and do some like lightweight zero copy or translation there, you can also target for the same goal. Yeah, as I said, there's a teamwork, a lot of people is involved. Yeah. Yes, my talk is stopped here, and then leave the time for the Q&A. Any questions? Yeah, Emma.
You mentioned the vhost file script in the user space implementation. Can you have server like this for a single guest?
For a single guest?
Yes. Like, or do you have any solution for the virtual IMMU?
Yeah, virtual IMMU, we haven't considered that yet because that now we can, on the host side, we are real device, so just to get the real IMMU into the picture, not put a virtual IMMU yet. Yeah. Any other questions? Oh, okay. If no other actions, yes. It's so much for my talk. Yeah, thank you.